Okay, in the last video, we were just starting the page 3 of activity 3 in HASBOT. What is the future of Earth's climate? So on page 3 in activity 3, we have this model looking at radiation gas interactions. The sun is emitting sunlight, it heats up the ground, and then it emits infrared radiation. If we turn on this, it will show you kind of a representation of how hot the molecules in the soil are getting. So what happens when the sunlight hits particles in the ground? So when the sunlight hits these particles, they absorb some energy. You can see their heat rating changes from like pink to dark red. And then let's stop this for a second. You can see them emitting these little squiggles here. These are that's infrared radiation. So it absorbs the light coming from the sun. The soil is absorbing the light, and then it's heating up the soil, and the soil is re-radiating heat as infrared radiation. Infrared radiation is just heat energy traveling as waves. So let's change this to the particles in the ground. Absorb the sun's energy. They get hot. They vibrate faster, which is what hot molecules do. As they cool, as the soil particles cool, they radiate heat in the form of infrared radiation. What happens when the sunlight hits the greenhouse gas molecules? Well, let's see the sun and CO2 here. It doesn't seem to be really interacting. There's nothing really happening. So the sunlight doesn't interact with CO2 or water vapor. So sunlight does not interact with CO2. It just goes right past. CO2, which is carbon dioxide molecules. So what happens when infrared radiation hits the greenhouse gas molecules? Does this temperature change as a result? Well, let's go watch the greenhouse gas molecules. So here's infrared. Infrared, remember, is heat re-radiated from the ground as it heats up. When that infrared hits one of these particles, you can see that particle heat up. There's like a little yellow circle around it. That particle will heat up, and eventually that particle will re-radiate that heat in a different direction. Let's watch closely. Watch these two yellow molecules. Keep an eye on this one. Eventually they lose their energy, and you can see that the heat goes off in a different direction. So watch this one, or let's watch. It's hard to pick one and watch it. Pick one of the red balls, the carbon dioxide, with a yellow kind of circle around it, and watch it. Eventually it'll cool down and radiate one of these. You can see this infrared is zinging off carbon dioxide that just got cooled down. So that is how the Earth, how infrared radiation interacts with the carbon dioxide. It heats up the carbon dioxide, it vibrates faster, and then eventually it'll cool and re-radiate that infrared in a different direction. And that infrared usually doesn't go up. It usually goes sideways or down and back into the Earth's atmosphere. The The infrared radiation heats up the CO2. The CO2 absorbs the infrared radiation when it heats up. And then eventually the CO2 cools down and will let go, or that infrared radiation will leave as the carbon dioxide cools and emits the heat back into the atmosphere. So we talked about kind of how the carbon dioxide acts as a blanket, and that's how it does. It holds in the heat. It absorbs the heat and then it re-radiates the heat back into the Earth's atmosphere. Based on the Earth systems model and the molecular model, how does the carbon dioxide and other greenhouse gases cause Earth's atmosphere to warm? Well, unfortunately, I already did this, and I've given you the right answers here. Carbon dioxide is one of the many different greenhouse gases. The greenhouse effect is what has made Earth so habitable for much of the life we see on a daily basis. The moon doesn't have much of an atmosphere, and so it's very cold. Earth has an atmosphere, so it's made it warmer. The greenhouse effect is a process in which heat coming from the Earth's surface is prevented from escaping into space by greenhouse gases. As a result, Earth's temperature is higher than it would be if the direct heating by the sun were the only warming. The greenhouse effect couldn't work without energy from the sun. So, those greenhouse gases absorb outgoing infrared radiation, and they also emit outgoing infrared radiation. So if this is the carbon dioxide in the Earth's atmosphere, it absorbs the infrared radiation, it hangs on to it, and then as it cools, it re-releases that infrared radiation, usually back to Earth, and that helps keep Earth warm. The problem is we have too thick and too much blanket right now. Describe the similarities between the molecular model and the Earth systems model. Well, let's look at the last model here. We can still see the Earth heating up here. If we let this run for a while, we know the Earth's temperature increases, and we can see that here. What's different in this model is we can actually see at the molecular level what's going on. We can see these particles vibrating more quickly, and we can see them let go of their heat energy as infrared radiation. So heat goes into the carbon dioxide in the atmosphere and is eventually released back into the atmosphere, so the CO2 acts like a blanket. In the molecular model, so with molecules, with particles like we just saw above, we can see the molecules vibrate faster and see how they give off infrared radiation or heat when they cool down. So it's a little bit more of a detailed model. Okay, now we have another Earth systems model. This doesn't look so much at the molecular level. We're looking kind of at the whole Earth as a system. So we can erupt and add more CO2. We can erupt this volcano here. Let's do that. Have to run the model here. Press play. We can erupt, and make lots more CO2. Or we can remove CO2. We can follow a single CO2 molecule. Make that easier to do as they kind of bounce around. We can see, it's easier to see how they reflect infrared radiation. If you follow this one molecule, you can see how it's interacting with those purple arrows and kind of turning them around. That represents heat being re-radiated or sent back to Earth. So hopefully y'all know at this point that the purple arrows are infrared radiation. What evidence do we have to support that? Well, in the model, we see the purple arrows bounce off carbon dioxide, and we know carbon dioxide is one of the greenhouse gases that absorbs heat and re-radiates it back towards planet Earth. So that's really good evidence that the purple arrows, the infrared radiation or heat, bounce off the green carbon dioxide molecules. We know carbon dioxide is a greenhouse gas that absorbs heat from Earth and releases that. So we have very good evidence to support that those purple arrows are infrared radiation or heat. So we're looking at atmospheric carbon dioxide over time. Carbon dioxide is a greenhouse gas that's directly affected by human activities. The amount of carbon dioxide in the atmosphere in modern times has been measured accurately since 1958. Charles Keeling measured the atmospheric concentration of CO2 at the top of Mauna Loa on the Big Island of Hawaii. The curve shows the amount of atmospheric carbon dioxide is also known as the Keeling curve. So we can see this is carbon dioxide. If we read the title, this is the amount of atmospheric carbon dioxide at Mauna Loa. It's not the temperature, it's the amount of carbon dioxide in the air. And we see this little seesaw pattern. From year to year, it just kind of goes up and down in a very regular pattern. Let's talk about why that happens. Here's a picture I took of Minnesota in the winter. Do any of these trees have leaves on them? Is there any CO2 being absorbed in this ecosystem right now? Maybe a little bit, because some of the trees have photosynthetic bark, but not much. And these evergreens are still photosynthesizing, but not as much as in the summer. Here's a different picture of Minnesota. You can see there much more photosynthesis going on. There's green leaves on the trees, there's grass, there's lily pads in the water here, there's bushes. There's much more photosynthesis going on in September than there is in February. So there's the difference in the ecosystems in the northern hemisphere. The amount of photosynthesis makes that seesaw pattern in the Keeling curve. So that seesaw pattern is winter, summer, winter, summer, winter, summer, winter, summer. Because the level of photosynthesis in the northern hemisphere goes up and down, and photosynthesis is really important for absorbing the amount of carbon dioxide. So what are some of the causes of carbon dioxide increase in the past 50 years? You can come up with your own. Primarily, we're burning fossil fuels. There are fewer trees because we've done a lot of deforestation, or we've had a lot of forest fires because of climate change that burn down our trees. A lot of people burn wood to heat their homes. A lot of people in developing countries use wood to cook their food. And all of that wood has to be cut down from trees that usually absorb carbon dioxide. We talked about question 19, where there's a lot of photosynthesis in the summer in the northern hemisphere, and that pulls the global carbon dioxide down, where in the winter there's not as much photosynthesis, so we have more carbon dioxide in the atmosphere. So how do we figure out the carbon dioxide levels a long time ago? The Keeling curve shows us about 50 years of data. The Earth is at an atmosphere for over 4 billion years. So how do we get some data on the past? It's not so recently that humans been able to measure carbon dioxide levels. How can we know what carbon dioxide levels were in the distant past? Atmospheric gases are stored in the spaces between ice crystals in snow and the ice of glaciers and ice sheets. Scientists drill holes in the ice to extract those ice cores. We saw ice cores earlier in this activity. Older layers of ice are at the bottom and the younger layers on top. When sections of the ice are melted in the lab, scientists can measure the amount of carbon dioxide and other gases that were trapped when ice formed. The levels of trapped gas are measured in parts per million. A measurement of 350 parts per million CO2, that means for every 1 million gas molecules, 350 of them are carbon dioxide. So it's a pretty tiny amount of carbon dioxide, but it's still very important in the functioning of our planet. Vostok Station is a Russian research station in Antarctica, near the South Pole. The graph shows the concentration of carbon dioxide in parts per million from ice cores. Note that the x-axis of the graph shows the time period over which the data were collected. The most recent data is collected 0 years ago, and the older ice core measurements are over here. So you can kind of think of this as an ice core laying on its side, where the oldest part of the ice core is going to be on the bottom, and the youngest part of the ice core is going to be on top. If you were going to dig a hole in your garden and you took a sample of the soil in a column, the soil that's on top of your garden would be at the top of that column of soil, and the soil on the bottom of your garden would be on the other end of that sample. It would be lower down. So this is the ice core data, and this is carbon dioxide versus age. They can directly measure the amount of carbon dioxide in the air bubbles in the ice cores. So this is not an implied measurement, it's a direct measurement. It's carbon dioxide. How many years of data are available from the ice cores? Well, right now, it doesn't go out to 450, but it goes just past 400,000. And here's 425, a little less than 425,000. So I think you can figure that one out. Question 21. What is shown on the y-axis of the graph? The y-axis is the vertical part, and let's read the label here. Atmospheric carbon dioxide in parts per million. So that should help you answer question 21. Read the label. Which year had the highest concentration of carbon dioxide? 0 years before present. That'd be right here. 50,000 years before present. That'd be right here. That doesn't seem very high to me. 325,000 years before present, which would be about right here. Or 400,000 years before present, which would be right here. Which one do you think is highest? This one, this one, this one, or this one? I bet you can figure it out. What was the carbon dioxide level at 355,000 years ago? So let's go on the graph here. Here's 350, 355 would probably be right about here. Let's go over on the y-axis. That's probably about 205. Let's see if that's an option. Well, they say 187. 375. So maybe 305 is about 355. Might be right here. So that might be right there, which would put us about at 187. The carbon dioxide levels falls between 50,000 years and about 30,000 years ago. What happens to the temperature between 50,000 years ago and 30,000 years ago? So here's 50,000 years ago. Here's 30,000 years ago. So between these two times, what do you think happened to the temperature? Carbon dioxide increased, but then eventually it went down. If the carbon dioxide goes down, what happens? If it goes up, we know what happens to the temperature. So think about what happens when you take carbon dioxide out. Will the opposite thing happen? So here's question 25. Temperature is related to the amount of carbon dioxide in the atmosphere. How does the temperature of 125,000 years ago compare to the temperature of 355,000 years ago? So let's go look at these on the graph. So this is about 355, and this is about 125. So here and here, 125, 355. High at 125 and very low at 355. So if we have high carbon dioxide, what's going to be the temperature at 125,000 years ago? That was high carbon dioxide. What do you think the temperature is going to do? This was very high carbon dioxide. We're comparing it to very low carbon dioxide here. The temperature 125,000 years ago, was it high? Was it lower than 355,000 years ago? Was it the same or was it higher? Explain your answer. Well, I'll let you pick an answer to question 25, but I'll have a little explanation for you. From the models we have used, we know if we add CO2 to the atmosphere, the air and sea temperatures rise. How certain am I about my explanation? Well, we have data from the ice cores that show the carbon dioxide was higher. A limitation on our certainty is we don't actually have temperature measurements. Whatever temperature measurements there are, the temperature measurements are inferred from the carbon dioxide. And an inference is you take what evidence you have and then you come to a conclusion. And since we have really good evidence from the ice cores, we can come to a fairly solid conclusion, but it's not perfect. We weren't there. So it wants me to answer here, so I'm going to guess higher. I'm going to submit. Ooh, I only got a 3 here. I need to answer some more of these questions. So I need to respond to the feedback. Feedback's great. It's like coaching. I have a coach for, I'm an athlete. I have a coach. My coach gives me feedback on how I'm performing as an athlete and helps me get better. We're going to get better at argumentation because we have feedback here. You can read the feedback and you can respond to that feedback. Can we provide specific evidence from the graph? Let's use some numbers from the graph. Add to my explanation. Why is atmospheric CO2 important in estimating past temperatures? What do we know about how infrared reacts with CO2 to increase Earth's temperature? How can we use some of our model data to support us? Can you explain what about the graph makes you certain or uncertain? Ice cores are just one representation of the carbon dioxide, so they're not perfect. And they're only one part of the world. So you can add some more explanations. You can read the feedback and you can add some more explanations of your own. And thanks for playing. The next video will be activity 4. This is Dr. B signing off.